So let's consider this modeling problem that we're left with a little bit more closely. And to do this, I'm going to use the following example. So if we consider this word base, there are many possible tags at this particular position for this word base. And we'll use script Y to refer to this set of possible tags. So we have, for example, singular nouns, plural nouns, transitive verbs, intransitive verbs, prepositions, determiners, and so on and so on. And our task is going to be to estimate the probability for any one of these possibilities given the context. So what is the context? The context is going to be the previous two tags, in this case determiner and adjective, and potentially any features of the sentence. So remember, we have P of Tj given W1 through Wn, the sentence, and then Tj minus 2, Tj minus 1. So we can condition on the previous two tags, and we can condition on any information in the entire sentence. And of course, this is a very complex object that we're conditioning on. There are many, many possible features of this context which could be useful. And that's really the motivation for using log linear models in this context. So to apply log linear models, we're going to have to develop a little bit of notation. And a critical idea is going to be the idea of a history, which basically captures all of the information in the context, all of the contextual information that we can condition on. And a history is going to be a for tuple consisting of the following. We have the previous two tags, t minus 2 and t minus 1. We have the entire sequence of words in the input sentence, W1 through Wn. And then we also need to be a little bit careful to make sure we condition on the position of the sentence that we are tagging. So I is going to be an index of the word being tagged, the position in the sentence. So let's see how this for tuple is instantiated for this particular example. In this case, we have t minus 2 and t minus 1 equal to the two tags dt followed by jj. We have W1 through N consisting of the entire input sentence, the entire sequence of words. And then we have the position I is equal to 6, because if we count the words in the sentence, we have 1, 2, 3, 4, 5, 6. This is at position 6 in the sentence. So again, this history basically captures all of the information about the context, the previous two tags, the entire sentence, and the particular position in the sentence. We'll use script X to refer to the set of all possible histories. So that's going to be a very large set, actually potentially an infinite set, a countably infinite set, if we allow sentences of all possible lengths. So given these definitions, we can apply a log linear model in a very direct way. And so here, again, is a recap of the idea of feature vector representations as used very directly in log linear models. So in general, in a log linear model, we're going to assume some set of possible inputs or histories. In our tagging case, this again is going to be a for tuple t minus 2, t minus 1, W1 through Wn, and some position I. And we also assume that we have some finite label set, which we use, which we denote by script Y. For example, this might be the set of all possible part of speech tags, maybe D, N, and V. Our aim is to provide a conditional probability Py given X for any history X combined with any label Y. So the key representational trick in log linear models is to make use of features. So a feature is a function that takes a history paired with a label and maps it to some value. And we saw last week when we considered log linear models that many of the features used in NLP are these rather simple binary features where the result of the function is either 0 or 1. These features typically ask questions about the input x in conjunction with the label y and return 0 if that question is false, 1 if the answer to that question is true. And then, given a set of m features, f sub k, for k equals 1 to m, we can define a feature vector to be a vector consisting of the m values of these m different features in the model. And so basically we end up with mapping a particular history or input paired with a particular tag to some feature vector which represents the output, the results of all of these features or questions about the history in conjunction with the label. So here are some examples of how we might instantiate features in the tagging problem. So we have x, the set of all possible histories of this form, y is the set of tags, we have various features. So the first example feature is the following. So f1 is going to be 1 if the current word wi is the word base and the tag t is equal to vt. So this intuitively is going to capture the affinity for that particular word base we were considering for having the transitive verb tag. Now this is just one feature, of course. You would, in practice, define many potential features, quite likely corresponding to every possible word paired with every possible part of speech tag. Here's a second type of feature, f2. And this says the following. It's going to be 1 if the current word wi ends in the suffix ing, and the tag is vbg. This is a gerund verb. This is the tag for a gerund in the Penn tree bank, for example. And words ending in ing in English are very often tagged as vbg. Now, you'll start to see something interesting happening here, which is that, in a sense, this feature is captured by the parameter in an HMM, which is e of base given vt. That is the natural parameter in an HMM which captures the affinity for the word base to be a transitive verb. But this really is a new type of feature which looks at some spelling feature of the word being tagged. In this case, the suffix ing. These kind of features are much more difficult for HMMs. And in fact, we saw in the programming assignment in this course, and actually in the lecture slides for HMMs, that one common way of dealing with these kind of spelling features was to introduce mappings from rare or infrequent words to maybe 10 or 20 different word classes. But that was really a rather crude way of doing things. It's much more convenient to be able to define features like this, which will look at the spelling in conjunction with the tag. And actually, those are two feature types from work by Adwait Ratnapaki, which was one of the earliest applications of log linear models to tagging. Actually, probably the earliest. And I can actually describe the full set of features he used in his model. So it's a pretty simple set of features, and yet it's still close to state of the art in that if you use these features in a part of speech tagger, for example, you will get a state of the art model. So he introduced word tag features. So features like the one I've shown you here that pair a particular word or the identity of wi as a particular word with a particular tag. And he included one feature like this for every word tag pair seen in your training example. So a quite large number of features which pair words with underlying tags. He also considered spelling features which looked at all prefixes or suffixes of length less than or equal to 4. Okay, so here is this example feature again, which looks at the suffix being ing in a particular tag. And here is a feature which looks at the prefix and fires if the particular word wi starts with the 3 letters pre, and the tag in this case is a common, or rather a singular noun. So again, we're going to consider all prefixes and suffixes of length less than or equal to 4, potentially combined with all possible tags which are possible, a quite large number of features. But these features are invaluable when you're dealing with infrequent or unknown words. These kind of spelling features can be very useful in disambiguating those words. Ratnaparky also looked at contextual features. So these first 3 features look very much like trigram, bigram, and unigram features over tags. So this first feature is 1 if the tag sequence t-2, t-1t is equal to dt, jj, vt, and it's 0 otherwise. So this captures a particular trigram of tags, and you would most likely have one feature like this for every possible trigram of tags, or at the very least one feature like this for every trigram of tags seen in your training examples. Here's a bigram feature. So this fires if the previous tag is jj and the current tag being proposed is vt, so that's a bigram of tags. And then finally we have a feature which just looks at a unigram, looks at the tag itself alone, t, and just fires on the fact that it's a vt. Now of course we're going to have parameters in our model, v103, v104, and v105, which are basically going to be in some sense correlated with the probability or likelihood of this trigram or this bigram or this unigram of tags. Ratnaparky also made use of features which, in addition to looking at the current word wi being tagged, so in general we might have, for example, this might be the word base, we can also look at words surrounding this, either to the left or immediate right. And so here's one feature, which is 1 if the previous word wi minus 1 equals there, and the tag equals vt. Or we might have a feature looking at the next word, the fact that wi plus 1 equals there, and the t equals vt. So you can see that the flexibility of log linear models allows us to define all kinds of features which look at the current tag being proposed as well as features of the context, whether those features are the previous 2 tags in the context or their surrounding words in this particular context.